people are here, or a lot of people are here. Let's go ahead and get started. So this section, so today we were going to cover these. I put this on the Slack. We're going to cover 582 to 591 pages and the sections sparse autoencoders through generating fashion MNIST images, and I think we'll be able to make it through that. I'll just put this on chat as well. So let's see, chat. There, and so we'll read for like 45 minutes starting at 6:40, so that will be 7:15 that we'll come back together.
Great.
And if you finish reading for early, then go ahead and play with the chapter, the notebook. Yeah, let's see, I put it on Colab. I guess I should share I can share my version. You probably have your own version already, but if you don't, you can just share mine. Let's see, it will be in the chat here. My copy of chapter. Oh, I haven't done very much to it, so it's pretty much the same as the original. So that's on the chat now, and I'll also put it in the Slack. All right, so we'll reconvene at, what did I say, 7? Oh, it'll be 7:25, right? Because 45 minutes, yeah, 7:25. There we go. All right. Oh, we're back. So how did that go? Did most people have a chance to get through most of that? Yes, no?
Yeah.
Yeah, it's okay.
I did.
Okay. Anybody feel like they really want a little more time? No? Good. Okay, so let's just go through the three sections then. The first thing is the sparse autoencoders, and he mentions that by forcing the autoencoder to into a sparse representation of the data, that's kind of a method of regularizing it, and so that's basically all the sparse autoencoder is just the autoencoder, the basic autoencoder that we've seen with an extra overlay of L1 regularization. So, oh, and the other thing that's different is that the encoding layer is now large. Remember, we had been working with underdetermined autoencoders, where the hidden layer is the last hidden layer is smaller than the inputs. So it first takes the 728 images, 784, sorry, the 28 by 28 images, which are 784, then it takes them down to 100. And then in the basic autoencoder that we studied before it, the next layer takes them down to 30 and then has a sigmoid at the end. But in this case, we're instead going to do an overdetermined layer, which an overdetermined network, which takes, instead of taking it from 100 down to 30, it takes it from 100 up to 300. But then it imposes regularization, L1 regularization. And he mentions that you can do it this way, where the regularization is a separate layer, or you could just incorporate the regularization into this layer, into this dense layer, by using, he said you could remove the activity regularization layer, which is this one, and just set this variable, set this parameter inside of here. So in other words, you would say layers.dense, 300 comma, my screen is playing tricks on me. I'm sorry about this. Okay. It doesn't want to go to full screen. Okay, let me just leave it this way then. You're still seeing it, right? Is my screen jumping around for you, or was it before? There it jumped again. Did you see it jump just then?
Yep, we can see the different section of your screen right now.
So you see the background here and the.
Uh, yeah, we can only see the certain section of your.
Oh, so the full page isn't shown right now, is what you're saying, right?
Yes, yes.
Yeah, that's what I see too. And I keep putting it up to full screen, and then it jumps on me, but we'll just see how that goes. So now you see the full screen, right?
Mm-hmm.
Okay, so what he was saying down here is that instead of adding an activity regularization layer, you could set a parameter here and just stuff it into the to this dense layer by just putting a comma after activation equals sigmoid, comma, and then pasting in this this parameter setting. Okay, but the main thing is you're inserting an L1 regularization layer. And I like the language he uses. He said, this penalty will encourage the neural network to produce codings close to 0. As we know, that's what the L1 regularization does. But since it will also be penalized if it doesn't reconstruct the inputs correctly, then it will have to output at least a few non-zero values. So we're not in danger of setting all the inputs to 0, because if it did, then it wouldn't be able to reconstruct the inputs at all. So using the L1 norm, it says it pushes the neural network to preserve the most important codings while eliminating the ones that aren't needed for the input image, rather than just reducing all the codings. That's what L2 would do. It would just reduce all the codings, make them all smaller. So that's pretty easy to understand. It's a pretty simple concept. We're just basically looking at our basic autoencoder with two tweaks. One is that it's an overdetermined layer instead of an underdetermined layer. So we bumped this up from 30 to 300. And then the second thing is we just added the L1 regularization. But as we always find out when we read Geron, it's never easy. He always finds another tweak that makes it even better. So the other tweak is to he says measure the actual sparsity of the coding layer at each training iteration, and then penalize it if it's not. You set what you want the sparsity to be, and then you penalize it if it's not close to what you want the sparsity to be. So as an example, he says, you could ask that the sparsity be equal to 0.1, and then you would penalize it if the actual sparsity is 0.3. You would penalize it. You would sort of one approach, he says, is adding the squared error to the cost function. So that's one way of penalizing it for not having sparse encodings. But then another tweak, he says, in practice, a better approach is to use the Coolback Liebler divergence. He said it's briefly discussed in chapter 4, and has much stronger gradients than the mean squared error. So here's what the Coolback Liebler, dang it, there it goes again. Back, okay. This is what the blue curve is, the Coolback Liebler divergence. I really got to find out what's going on here. Maybe if I don't touch the mouse. Nope, that didn't work either. Let's see. What if I just do it this way? Please move this window. I'm not sure why it's doing that. Anyway, so you can see that the blue curve is the KL. It's called the KL divergence, the Coolback Liebler divergence, and we'll learn about it. It's a bit of a mathematical topic to look at. So he shows that against the L1 and the L2, and he shows this curve showing why the KL divergence is better, because it penalizes sparsity more than the L1 divergence. Than the L1 than the mean absolute error. Okay, so let's learn about the Coolback-Liebler divergence. You can represent it in this form, DKL. This is a common way they represent it. DKL of probability, and then this double bars, and then some other distribution that you're comparing it with, is just the sum of the probabilities It's the probability distribution of this log term is what it is. And the log term is the ratio of the target probability to the actual probability. I believe that's what the order of P and Q are. So in this case, P is the is the target sparsity, and Q is the actual sparsity. Let's see. Once we have computed, we sum up the losses and add the result. So he has this thing that he calls the latent loss function that he adds to the ordinary loss function. I guess he calls it the sparsity loss function. Summing up the sparsity losses for each neuron and add the result to the ordinary cost function. And you can, just as with other regularization techniques, that you can introduce a parameter that allows you to determine that, a hyperparameter that is, that allows you to determine how much regularization of this kind you want to impose. So if you set the regularization parameter high, that means you're going to place a lot of weight on this, on getting the match to the sparsity that you wanted, and not very much weight on the reconstruction error itself. And so that's what he says here. If the weight is too high, the weight being the the regularization parameter, then the model will stick closely to the target sparsity, but it may not reconstruct the inputs properly because it's emphasizing the sparsity part of the loss function. So that's kind of useless. And conversely, if it's too low, then the model will mostly ignore the sparsity objective and will not learn any interesting features. So we've all seen that before, where you introduce a regularization parameter to control how much regularization we want. Okay, so I want to go to, because Coolback Liebler divergence is really interesting and it's also important. It comes up whenever you want to force two distributions to match each other. So you want to tweak things until the distributions match. The loss function to use is always the Coolback Liebler divergence. And it just so happens that Jaron made a video about this. I think I don't know where he refers to it in the textbook, but it is one of the resources for the course. So it's only 10 minutes, so let's listen to that at this point. Are there any questions before we do? Okay, let me put it up to full screen.
Hi, my name is Aurélien Géron, and in this video, I'll try to give you a deeper understanding.
I need to rewind it. And I'll play it for a few seconds and let me know if you're getting the sound.
Entropy, cross-entropy, and KL divergence
actually
are. In machine learning, cross-entropy is very commonly used as a cost function.
You are getting the sound. Well, that's good because I'm not getting the sound. Anyway,
those concepts
I think the way I can get it is to take off my
information theory. Shannon was an American mathematician, electrical engineer.
I'll do that. Switch my sound. Switch my sound to. Okay, let me try it and see if I can hear the sound.
And cryptographer, and in his 1948
You're hearing
paper,
sound?
Mathematical Theory of Communication, he founded what is now known as information theory. The goal is to reliably and efficiently transmit a message from a sender to a recipient. In our digital age, messages are composed of bits. Of course, you know that a video, I'll try to give you a deeper understanding of what entropy, cross-entropy, and KL divergence actually are. In machine learning, cross-entropy is very commonly used as a cost function when training classifiers, and so we'll see why that is. Those concepts come from Claude Shannon's information theory. Shannon was an American mathematician, electrical engineer, and cryptographer, and in his 1948 paper, Mathematical Theory of Communication, he founded what is now known as information theory. The goal is to reliably and efficiently transmit a message from a sender to a recipient. In our digital age, messages are composed of bits. Of course, you know that a bit is a number that is either equal to 0 or 1. But not all bits are useful. Some of them are redundant, some of them are errors, and so on. So when we communicate a message, we want as much useful information as possible to get through. In Shannon's theory, to transmit one bit of information means to reduce the recipient's uncertainty by a factor of 2. For example, say that the weather is completely random, with a 50-50 chance of being either sunny or rainy every day. If a weather station tells you that it's going to be rainy tomorrow, then they have actually reduced your uncertainty by a factor of 2. There were 2 equally likely options, now there's just 1. So the Weather Channel actually sent you a single bit of useful information, and this is true no matter how they encoded this information. If they encoded it as a string with 5 characters, each encoded on 1 byte, then they actually sent you a 40-bit message, but they still only communicated 1 bit of useful information. Now, suppose the weather has actually 8 possible states, all equally likely. Now, when the weather station gives you tomorrow's weather, they are dividing your uncertainty by a factor of 8, which is 2 to the power of 3. So they sent you 3 bits of useful information. It's easy to find the number of bits of information that were actually communicated by computing the binary logarithm of the uncertainty reduction factor, which in this example is 8. But what if the possibilities are not equally likely? Say 75% chance sunny and 25% chance rainy. If the weather station tells you it's going to be rainy tomorrow, then your uncertainty has dropped by a factor of 4, which is 2 bits of information. The uncertainty reduction is just the inverse of the event's probability. In this case, the inverse of 25% is 4. Now the log of 1 over x is equal to minus log of x. So the equation to compute the number of bits simplifies to minus the binary log of the probability, 25%. Now, if the weather station tells you it's going to be sunny tomorrow, then your uncertainty hasn't dropped much. In fact, you get just over 0.41 bits of information. So how much information are you actually going to get from the weather station on average? Well, there's a 75% chance that it will be sunny tomorrow, so that's what the weather station would tell you, and that's 0.41 bits of information. Then there's a 25% chance that it will be rainy, in which case the weather station will tell you so, and this will give you 2 bits of information. So on average, you will get 0.81 bits of information from the weather station every day. So what we just computed is called the entropy. It's a nice measure of how uncertain the events are. Hopefully the entropy's equation should now make complete sense. It measures the average amount of information that you get when you learn the weather each day, or more generally, the average amount of information that you get from one sample drawn from a given probability distribution P. It tells you how unpredictable that probability distribution is. If you live in the middle of a desert where it's sunny every day, on average, you won't get much information from the weather station. The entropy will be close to 0. Conversely, if the weather varies a lot, the entropy will be much larger. Okay, now let's talk about cross-entropy. It is really quite simple. It's just the average message length. For example, if the weather station encodes each of the 8 possible options using a 3-bit code like this, then every message will have 3 bits. So the average message length will of course be 3 bits, and that's the cross-entropy. But now, suppose that you live in a sunny region, and the weather's probability distribution looks like this. Each day, there's a 35% chance of being sunny, and only 1% chance of thunderstorm. So you can compute the entropy of this probability distribution, and you will find that it is equal to 2.23 bits. So it's a shame the weather station is sending 3 bits per message on average when the weather's entropy is just 2.23 bits. In other words, on average we send 3 bits, but the recipient gets only 2.23 useful bits. We can do better. For example, let's change the code like this. We're now just using 2-bit messages for the sunny or partially sunny weather, 3 bits for the cloudy and mostly cloudy, 4 bits for light and medium rain, and 5 bits for heavy rain and thunderstorm. Note that our code is unambiguous. If you chain multiple messages, there's only one way to interpret the sequence of bits. For example, 0, 1, 1, 1, 0, 0 can only mean partially sunny followed by light rain. Okay, so if you compute the average number of bits that we send every day, you get 2.42 bits. That's our new and improved cross-entropy. It's better than our previous 3 bits, but it's still not down to 2.23 bits. Anyway, now suppose we use the same code in a different location where the weather is reversed. It's mostly rainy. Now, if you compute the cross-entropy, you will find that it is equal to 4.58 bits. Wow, that's really bad. It's roughly twice the entropy. In other words, on average, we will send 4.58 bits, but only 2.23 bits will really be useful to the recipient. We're sending twice as much information per message as is necessary. This is because the code we are using makes some implicit assumptions about the weather distribution. For example, when we use a 2-bit message for sunny weather, we're implicitly assuming that it will be sunny every 4 days, 2 to the power of 2, at least on average. In other words, by using this code, we're implicitly predicting a probability of 25% for sunny weather, or else our code will not be optimal. So now it's pretty obvious that the predicted distribution Q is quite different from the true distribution P. Note that our code doesn't use messages starting with 1111, so that's why if you add up all the predicted probabilities in this example, they don't add up to 100%. Anyway, now we can express cross-entropy as a function of both the true probability distribution P and the predicted probability distribution Q. As you can see, it looks pretty similar to the equation for the entropy, but instead of computing the log of the true probability, we use the log of the predicted probability, which is equal to the message length. If our predictions are perfect, that is, the predicted distribution is equal to the true distribution, then the cross-entropy is simply equal to the entropy. But if the distributions differ, then the cross-entropy will be greater than the entropy by some number of bits. This amount, by which the cross-entropy exceeds the entropy, is called the relative entropy, or more commonly, the Coolback-Liebler divergence, or KL divergence. So in short, cross-entropy is equal to the entropy plus the KL divergence. Or equivalently, the KL divergence, which is noted dKL P to Q, is equal to the cross-entropy HPQ minus the entropy HP. In this particular example, the cross-entropy is 4.58 bits, and the entropy is 2.23 bits, so the KL divergence is 2.35 bits. Okay, now let's use cross-entropy in machine learning. Say we want to train an image classifier that will detect some animals. For each of the 7 possible classes, the classifier outputs an estimated probability. This is the predicted probability distribution. Now, this is a supervised learning problem, so we know the true distribution. In this example, we know that this is an image of a cute red panda, so the probability is 100% for red panda and 0% for the rest. We can use the cross-entropy between these two distributions as a cost function. This is called the cross-entropy loss, or simply the log loss. And it's just the equation we saw earlier, except it usually uses the natural logarithm rather than the binary logarithm. This doesn't change much for training, since the binary log of x is just equal to the natural log of x divided by a constant, the natural log of 2. So when the labels are one-hot vectors, meaning one class has a probability of 100% and the rest are 0, as is the case in this example, then the cross-entropy is just the negative log of the estimated probability for the true class. So in this example, the cross-entropy is minus log of 0.25. You can see that the cost will grow very large if the predicted probability for the true class is close to 0. But if the predicted probability is close to 1, then the cost will be close to the true distribution's entropy, which in this case is equal to 0 since it's a one-hot vector. And that's it for this short presentation of entropy, cross-entropy, and KL divergence. I hope you found it interesting. If you did, you know the drill. Please like, share, comment, subscribe, follow me on Twitter, and so on. If you want to learn more about machine learning, deep learning, and reinforcement learning, check out my book, Hands-on Machine Learning with Scikit-learn and TensorFlow. And that's all for
We can't hear you, Joseph.
Are you not hearing?
Now we can hear you.
Oh, now you can hear. Oh, sorry. Okay, yeah, so I think this gave us a really good introduction to, or a good overview of this concepts of entropy, cross-entropy, and KL divergence, and how they all relate, how they're all related. As you can see, if you break this out, log P over log Q is just log P minus log Q. So this is going to be the sum of the P log P minus sum of P log Q. So the first term would be the entropy, and the let's see. No, I guess let's see, minus. Yeah, there's a minus sign somewhere. But the point is that the P log P term is the entropy, and the P log Q term is the cross entropy. And the difference of those terms is the KL divergence. And when you when the when the predicted distribution is close to the actual distribution, then the difference will be 0, and the KL divergence will be minimized, and that's what you want to do in a problem like this. So now he just takes the KL divergence and gives an expression for each neuron. You know, so for each, so suppose you have a predicted, suppose you have a desired, a target sparsity that you want, and you call it P. In the example he gave, he said P was 0.1, and then Q is the average sparsity for that neuron. You know, for all the, I guess the average sparsity for all the weights associated with that neuron, and the sparsity by definition, he says, is the fraction of non-zero weights. Right, that's what he means by sparsity. So Q is the mean sparsity for a given neuron. And so you can actually construct this function, and that is the KL divergence. And then we just put that into the loss function. And then he does that over here. Let's see, KL divergence, KL regularizer. I think he builds this class here. And let's see, one minus self.target, one minus mean activities. So this is like the 1 minus Q, and this is the 1 minus P. So this is the, sorry, it's the KL divergence calculated from P and Q. And then this is the KL divergence calculated from 1 minus P and 1 minus Q, back over here. See that? So this is the KL divergence of P and Q, and this is the KL divergence of 1 minus P and 1 minus Q, as you can see from this formula, right? So all he does here is he's constructed a little class that does that calculation, and then using it, let's see. This is what he calls the regularizer, and let's see, K is Keras back in. KL divergence is, so it has a built-in KL divergence, Coolback Liebler divergence function in it. The loss function, that is built in. KL divergence regularizer of. Okay, so building the autoencoder using KL divergence regularizer of weight equals 0.05. I think that's the regularization factor. It's a regularization hyperparameter, and target equals 0.1 is the target sparsity that you want. So what this means is that the loss function is going to be the ordinary loss function plus 0.05 times the KL divergence loss function. Does that make sense? That's what that weight parameter is. It's basically the regularization parameter. All right.
Joseph, before we proceed, few questions.
Sure.
Can we go back?
How many pages? Where? Is this where you wanted to go?
Yes, please. The paragraph over there, kind of figuring out what exactly does he mean by sparsity.
Yeah, he makes a definition of sparsity earlier in the text, and as I mentioned, the sparsity is the ratio of non-zero weights to total weights associated with a given neuron.
Okay, so that makes sense. But then the comparison that he's making is average activation of 0.3, but the target sparsity. Like you're taking actually just one neuron and you're saying that as an activation of 0.3, but you're comparing it with the ratio of activated neurons for to ratio of non-activated neurons.
Sorry, I lost some of your audio there. Let me get my headphones back and then.
Yeah, okay. Yeah, I can hear an echo too for some reason.
Hold on for a second. Let me just get my headphones back and. Okay, I should be connected now. Can you hear me?
Can you hear me now?
It's still coming over my speaker. Let me try this one more time. For some reason, the Bluetooth isn't working right. Turn it off, turn it back on. Connect. And okay, I should be connected now. Yeah, can you hear me now?
Yeah, I can hear you. Are you able to?
It's still not on my, okay, let's just go on without the, yeah, let's just go on using my computer speakers. So can you repeat your question, please?
Yeah, so sparsity, what you define the echoes back. I don't know what is. Are you able to hear me?
It's fading in and out.
Like it's hard to comprehend what you're saying because there's an echo.
Yeah, I'm not sure. Now you spoke, I'm hearing an echo. I think it's coming from Joseph.
The echo?
Yeah.
It's probably because I need to get back on my headphones. Let me try this one more time. Disconnect.
Something you did in between, I think, when you disconnected the echo.
Yeah, I just disconnected Bluetooth, so that should have taken care of the echo. Did it?
Let's see. Yeah.
Okay.
No, I think that's back.
No. Okay, hold on for a sec. I'll get onto my. Change my microphone too. How about now? That changed.
Is there an echo? Yeah, I think that's better.
Okay.
Yeah, I can hear you too. Okay. So shall I repeat my question?
Yes, please.
Okay. So sparsity, yeah, like you defined, it's basically those ratio of activated neurons to like the unactivated or the neurons close to zero. And
the ratio of activated neurons to total neurons, I think.
Okay, right. Okay, to the total neurons, right. But here, when he's making that comparison, he's talking average activation of 0.3, but the target sparsity of 0.1. So target activation here is not that 0.3% of the neurons or 30% of the neurons are activated, right?
I see what you're saying.
Different things here.
He's comparing, it seems like he's comparing apples and oranges, right? Let's back up and find his actual definition of sparsity. I think I said it wrong because sparsity should mean the ratio of unactivated neurons to total neurons, right? Because sparseness means lots of zeros. So high sparseness should mean high ratio, a high proportion of zero of unactivated neurons, or this seems to me, let's just back up and find that in the text. Can somebody put their finger on where he defines sparsity? There it is. Oh, I thought I came across his definition of sparsity somewhere. Maybe it's earlier in the text. Maybe if I do a search. Can I do a search? This is really, let me go back in my paper book and see if I can find it. Because the cloud reader interface is really crappy. Let's see.
I don't see a definition anywhere.
Sparsity says it's on 582, and that's where we were. So
right, that just says to good feature extraction, you can use like sparsity by adding an appropriate. That's what you were saying.
yeah, so he never did really define sparsity. He kind of leaves it up to the imagination, but
But I would imagine like you're targeting sparsity, right? The whole idea of this sparse autoencoder is you want fewer neurons to be activated.
Yes.
You kind of learn.
So, yeah, well, I suppose the definition that I mentioned first is right. It's just the fraction of activated neurons over the total neurons, right?
That makes sense, yeah.
Yeah, and so when he uses the word, he's using two different words, which is confusing, but I think he means the same thing here. He says an average activation of 0.3. I think by that he means an average sparsity of 0.3.
No, actually, he is measuring the activation of each neuron and calculating its mean to be 0.3. And in this case, it seems that when he says target sparsity, then he's changing the definition there to match the average activation of a neuron to be 0.1, because otherwise, as Rakel pointed out, it will be apples to oranges. So
okay, that makes sense. So the definition that he's implicitly using is the average activation of the neuron.
right.
That's what you're saying. Okay.
That's what he's comparing in this case, even though I think that's where the language that Rakel is pointing to is confusing, because earlier he might have used sparsity to mean what you said, which is less number of neurons getting activated. But one could mean the other. But in this case, 0.3, when he's comparing to 0.1, it means that the average activation of a neuron should be less than some value where the target is 0.1.
Yeah, excellent. So well spotted. I think I just want to say that Rakel pointed out a very, Rakel spotted a problem in the text, and in Srinivas, you've solved the problem. I mean, basically the problem looked like our notion of sparsity wasn't consistent with the average activation. So, and then Srinivas said, well, maybe what he means implicitly by sparsity is the average activation. And so when you say you want your network to be sparse, you set a parameter for how sparse you want it to be. You want the average activation to be 0.1. And then you look at what the actual average activation is and compare it, and then that gives you a loss.
So actually going back one more page, you see what I think Srinivas is pointing to makes sense with, he says we need to use a sigmoid layer so you can kind of squeeze everything between 0 and 1. So hence that basically is talking about the activations. Can't be the percentage of the neurons there, right?
Sorry, and could you repeat that?
So when he's specifically telling us to use the sigmoid so that the activations are between 0 to 1. So that's how you're kind of reducing the, it's not increasing more than a 1, or it's not going out of bounds in that sense. So that's where he's talking about activation. But the confusion is if you go forward to figure 1711, there he again seems to be talking about number of neurons and not the activation.
Yeah, I kind of puzzled over this thing. These two things are different, but it's kind of hard to see that. So what you just said, Rakel, is that by using the sigmoid activation function, we make sure that all the activations are between 0 and 1, and then we can know what to sensibly set as an average activation. Like 10% sounds like sounds like it should be reasonably sparse. So that's one point that you make. And the other point is, let's look at this figure and try to understand what it means. So here he's plotting the distribution of all the activations in the coding layer. So this would be like 300 neurons, right? And the percentage of activations that are between 0 and 0.1, that's this bar. It's basically a histogram of activation levels. And there are 300 neurons that are contributing to this histogram.
Right.
And so if you remove the percentage of activations, then you would, if you make this number of activations, then all the bars would have to add up to 300. Okay, now let's look at the right-hand graph, which says we're plotting the distribution of the mean activation per neuron in, let's see, The mean activation per neuron.
So he's run the program 2 times, right? That's how you're calculating mean activation of the neurons. And this is not specifically just for the coding layer, but for the whole network. So that's like 300 plus the previous layer's 100 plus whatever I think the network is in this case.
Yeah, but there's only one layer that has sigmoid activations. And so I don't think this applies to the other layers, just to the coding layer.
If you look at the text, I mean, that's what I was highlighting is the paragraph just about the figure. It says, after training this Sparse autoencoder on Fashion and NIST, the activations of the neurons in the coding layer are mostly close to 0. So that's basically that last layer that we were talking about, that 300 neurons that spits out, yeah. 70% of all activations are lower than 0.1. And if you connect with 0.1, that 0.1 was the target sparsity that we were kind of talking about right now in that previous example.
So 70% of the neurons are here, and they meet the target sparsity, and the other 30%.
So then again, it's kind of like, if you're talking about number of neurons then, right? It's the number of neurons which have activations less than 0.1.
So that's 70% of 300 or something like that, right? So yeah. 200 neurons.
And then it goes on to say, and all neurons have a mean activation around 0.1. So I assume that all neurons meant for the rest of the net, I mean, including this layer and the rest of the network.
I guess I have a problem with that because we've only normalized the activations for the codings layer. So those are the activations that we.
X-axis is not activation, right? X-axis is percentage of neurons in this case.
I see. X-axis on the left is activation, and the X-axis on the right is the mean activation.
I'm sorry, the Y-axis is percentage of neurons, not percentage activations.
Right. So neuron mean activation.
Yep. Just to clarify, if we look at the link that I've shared, there's a paper, and it has beautifully visualized this, how each layer is activated. So we can get an intuition of this diagram, this graph from there too.
So, am I sharing the right thing? This deep sparse rectifier neural networks, is that the paper that you?
Yes.
Okay.
Am I deep sparse rectifier?
Am I?
No, we cannot see it right now. Yeah.
Let me share it to stop share, and then share the right thing. So let's see, share screen, and I see this. Sharing it now?
Yep.
Yeah.
So where do we want to look?
On the third page.
Actually, I should have let you share. Anyway, that's page 2. That's page.
Yes. This is the figure 2.
Figure 2. Okay.
So here we can see the percentage of activations. If we have hidden layer 1 that has 1, 2, 3, 4, 5, 6 neurons, and only 2 are being activated, and that's the what we can see from the overall mean and the activation if we go back to the book. So this is the dense layer, which has the KL divergence and the activations being applied by the target and the mean activities. And the percentage of activations here will be 2/6, because that's the number of neurons that have been activated. And each neuron will have activation rate of around, what do I say, that will be 90%. If I Right from the diagram, from the from the figure of the book, the figure 1711, distribution of activations.
Okay, shall I go back to
Yeah,
that? So
yeah.
what Rekil said is that he thinks that that is referring to the cumulative neurons in the whole network. So that might be what we're doing. Let's see, stop this share and go back to the other share. Let's see.
You can share a screen and then switch
Oh, you're right.
between
I can
those
switch
two.
between them. Okay, thanks. I'll do that. Yeah, I noticed. I learned that trick from you actually, because I saw you doing it. Let's see if I can. There we go. Share that. And then this. Sorry, I'm just fumbling around here getting this done, getting this in the format that I want. Let's see. Okay, almost there.
Meanwhile, Rekil, if you go back and look at the paragraph where he starts with going back, another approach which often yields better results, then you begin to see how he is actually redefining, in this instance, sparsity to be the mean activation of per neuron and then the difference and lowering that. Sorry, there is an echo again.
Yeah, I mean, if you look at
This is the figure that, can you see everything? This is the figure we were talking about. And then this is the figure that Mayank pointed out.
right, we can see both.
You can see both, good, okay.
Yeah, I also think it should mean, I mean, if you look at the flow of the text, it's moving from L1 regularization, and we're saying we can use KL also as a better approach. And L1's job is to like kind of nullify certain neurons. So that feels like it's like a neuron count. I don't understand why this activation term is coming in between. Like obviously it's playing a role, but I'm not able to understand clearly how the activation is also playing a role in this.
It's actually only the activations, not the neuron count. The activations, by hammering down on the activation and making them very low, a large majority of them don't even activate, which is the goal. That's kind of what he's eventually after. So he's completely, even though he uses the word sparsity, and in this instance, it's by targeting very small activation, a large number of the neurons don't even activate. And then it's just the average activation difference. And you could, he explains how when he defines a sparsity loss, how you could just use the square of the difference between the mean activation of a neuron and your target activation for any neuron, which is 0.1 in our case. And then he says, but instead of using the mean difference of activations, use the Coolback Liebler divergence, which will give you a better shaped curve because it's between target distribution of the activation of the neurons and the desired distribution of the activation. And
okay. So you're
right,
saying
so
if there are like 500 neurons and you say that you want to cap the activation at 0.1, then there's a good percentage that a lot of them will end up close to zero, and hence that's where that sparsity term comes in loosely.
Correct. Exactly. Okay. He's changed it completely to just the difference between mean activation and target activation.
I see. Okay.
So, so in the left-hand side, doesn't it look like the left-hand side is doing a better job than the right-hand side? Because if our target is 0.1 and most of the neurons have a higher activation, in fact, almost all of them have a higher activation, then that's not doing a very good job on the right-hand side.
No, in fact, it says that 90% of have a mean activation around 0.1.
Well, it looks like 90% have a mean activation between 0.1 and 0.2.
0.2, yeah.
Unless, unless the thing is off and it means, and that bin is supposed to be centered on 0.1. I don't
Now,
know.
again, keep in mind that the mean, he defines the mean as the mean over, he defines the mean as the mean over the batch, over the complete batch. And that's something else that if you go back in his text, that's important to recognize, that the mean activation is saying, that's why he says that the batch size shouldn't be too small, because the mean will not be representative of the mean of the entire data. He says that as well. So the mean, so when he's pointing out the mean on the right-hand graph, it's not it's across the entire batch.
Okay.
And in fact, he calls his entire batch, which I assume to mean all of the data, because the entire batch or all batch language is confusing, because it doesn't mean,
Yeah, so it's either the mean over batch or the mean over all the data, but do you think it also refers to only the output neurons, or do you think it refers to all the neurons?
That I don't know.
Yeah. And so, yeah, so it's a little bit unclear, and I don't think it's our fault for not understanding this well. I think he just didn't express himself as clearly as he could have. So I think we should just move on. And it's good that we brought this up and discussed it, and maybe have an idea why, what's the difference between these two plots. As Srinivas pointed out, the mean must have something to do with all the data in a batch or all the data in an epoch, one or the other.
Can we go back to figure 1710? I had one more question.
Oh, go back to which one?
1710, the one before this.
Yes.
Looking at that figure, looking at this figure, if you look at the last line just above that figure, it says chapter 4. After that, it says KL, which has a much stronger gradient than mean squared error, as you can see in figure 1710. So what exactly are we seeing in that figure that corresponds to that statement?
Okay, the red is the mean squared error, right?
Right.
The blue is the KL divergence, and he's basically just saying that the KL divergence is steeper. It's got a steeper slope than the mean squared error, which means it's penalizing sparsity much more strongly than mean squared error. So for example, here you get, what about if you have a sparsity of 0.4? The mean squared error only penalizes it by this much, but the KL divergence penalizes it by this much. And then, but the most important part is out in the wings, where if the actual sparsity is 0.8, let's say 0.6, let's say, because that's in the regime where the KL divergence is bigger than both the L1 and the L2 terms.
Right.
The gradients are sharper, right, for the KL divergence. The gradients are much sharper.
Yeah.
Are we looking at the gradient here, or are we looking at the sparsity versus loss function?
We're looking at the gradient of the loss function, the gradient of the cost. And so the cost versus KL divergence is this blue curve, and the gradient is the slope of the tangent at any point, right? And it's steep, as you can see, compared to the mean squared error. The slope of the tangent at any point is shallower. That's all he's saying.
Okay. Okay.
And therefore leading to a higher penalty, because this function itself it rises more rapidly than mean squared error.
Right. Okay. Yep. That sounds good.
Okay. Next we have variational autoencoders. I just have to say that this material just is so cool. Can you still see it? Did I blow it up correctly?
Yeah.
Okay. Good. So the variational autoencoder is kind of like a variation on the autoencoder, pardon the pun, and it's back to 2013. So, if you're just starting machine learning now or deep learning, we have a lot of catching up to do. So the variational autoencoder has two differences with what we're used to. One is it's probabilistic, which means that their inputs are partly determined by chance. And we've seen that already in this denorming autoencoder. But in this case, it's true even after training. And in the prediction phase, you still the outputs are still partially determined by chance. So that's the difference, one difference between the autoencoders we've seen so far. But the other difference is that the variational autoencoder is generative in the sense that they can actually generate new data by pulling from, since it learns the distribution of the data, and so it can pull samples. It can actually pull samples, produce samples. It can sample from the distribution of the data because it learns that distribution. And that's the difference with the encoders that we've seen up until now. And in fact, this is the first time we see a generative model. The next one, the first one is this a variational autoencoder, and the next one we'll see in this chapter is the generative adversarial network. Both of them can generate new data that looks like both of them basically learn the data distribution and then can pull new samples from it. And you've seen this. I think Gans, he says, do a better job of it, but you've seen this website where this is not a real person, right? Where they just generate infinite number of faces that look totally realistic from the database that they have. And so that's why generative networks are so exciting. And also, you can do the same thing with music. You can learn the distribution of I don't know, a certain genre of music like chamber quartets or whatever, and then you can generate your own, generate something that sounds like a chamber quartet or whatever. So that's a really exciting area of machine learning, at least for me. So this is the schematic of what it looks like. The encoder and the decoder look the same, except there's this layer in between where you have a mean and a standard deviation that you've learned from your data, and then you add Gaussian noise. So you sample from the mean, and then you sample from the mean, then you sample from the standard deviation, then you pull a sample from a Gaussian distribution with that standard deviation. That's this part. And then you then you add them together, right? You take the mean and then you add a perturbation to it that's drawn from the Gaussian distribution. And the idea is, let's see, annotate like this. Yeah. So you have a Gaussian distribution that has some mean mu. Oops, sorry, I just lost my. Come on, don't do that to me. Get rid of this thing. This thing is just too clever. Too clever for me. Get rid of this thing. No, just go away. Okay, thank you. So Gaussian distribution with a mean mu, standard deviation sigma, and so this is this is meant to be sigma, this the width of the distribution. And so to sample from the Gaussian distribution means you choose you choose something, you choose a sample along here. And it's going to be mu plus some draw of sigma. So, if sigma is 1, the standard deviation is 1, then you draw from a distribution with a standard deviation 1, and you'll get something that's maybe a half, or it could be 2, or it could be 0.75 or whatever. And then you add that to the mean, and then that gives you a sample, right? So that's one. That would be one sample. Then you draw again from this standard deviation sigma, a Gaussian distribution with standard deviation sigma, and then you add it to your mean, and then you can just draw as many samples of this as you want. You're sampling the Gaussian distribution. So that's what they mean by adding Gaussian noise. And then And when you do that, so you're taking the input distribution and you're forcing it to look like a Gaussian distribution.
Joseph, I have a question.
Yeah.
Is it that we are making the target distribution the Gaussian because of what we use as the target distribution in the KL loss that we get in this case the distribution to be the generated distribution to be Gaussian, or is it because we are introducing Gaussian noise? I thought that the reason we get a Gaussian distribution as the output of the encoder is because the KL divergence loss has a loss term which makes the desired target distribution much like the desired sparsity target of 0.1 here. Instead of a target value, it's a target distribution.
Yes, but I don't think that's the reason. I think the reason why we're sampling from a Gaussian is because we know how to sample from a Gaussian. I mean, if we had our druthers, we would rather sample from this distribution. We just don't know how to. So we're trying to do the next best thing, and this is what he means by approximate. He says somewhere that we're doing approximate Bayesian inference. If we could sample from this guy, then we would be able to do much better job at it. And I think there is a branch of machine learning now. It's called normalizing flows. I haven't had a chance to get into it, but it allows you to do exact sampling from the target, from the data distribution.
Right, but what I was after is, can your target distribution be something different than a Gaussian if you used a different target distribution in your, if there was a way by which you could use a different distribution as part of the loss in your KL divergence loss? Because I just want to understand where the Gaussian distribution comes from. Is it from the fact that my assumption is that it is not coming from the fact that we are using Gaussian noise. It's coming from the fact that we have a target distribution as part of the KL loss, which is Gaussian. Is that true or not true?
My understanding is that we're sampling. We want to sample from a noisy distribution, and the only noisy distribution that we know of, or the easiest one to sample from, is a Gaussian noise. If we had some reason to believe that the noise was not Gaussian, and we had maybe it was binomial or something else, then we could put a binomial sampler instead here.
No, but my question is, you seem to be implying that the noise that we provide there is what determines the coding mu and rho determine a Gaussian mu and a rho, right?
Yes.
And I'm saying, is the reason for the output emerging from hidden 2 being Gaussian, is it because of the desired target distribution of our variational autoencoder being Gaussian, which is provided by the value of the other loss that we provide to KL divergence being a Gaussian distribution, rather than the noise that we are introducing being Gaussian?
Okay, I guess I don't understand what the KL divergence has to do with Gaussian noise. I mean, it's like we're approximating. To me, we're approximating the codings. We can approximate the codings by saying they have a mean of mu and a standard deviation of sigma, and that may or may not be right. I mean, the codings, in fact, you can see they don't. We're just sort of saying, well, if we pretend like it's a Gaussian distribution, then we can go the next step and sample from the noise.
Right, but the pretension of what distribution it's giving, what determines that is my question. What determines the pretense being Gaussian? Is it just, my assumption reading through was, if you read the paragraph, it say that the latent loss that pushes the autoencoder to have codings that look as though they were sampled from a simple Gaussian distribution. And then he says it's the KL divergence between the target distribution, the the Gaussian and the actual distribution of the codings. So that's why my assumption reading through this was, or is, that it's the latent loss value that we provide for a target distribution is the Gaussian distribution. That's why the distribution that it tries to generate is that of a Gaussian. Is my understanding correct, or is that not correct? That's my question.
Well, let's think about it. I don't have an answer to that yet. Where is it that you're reading from? Is it on the next page or?
I think so. It will be much more clear if you look at the code of the variational encoder. When they are creating the encoder, they have used the coding mean, the coding log variance, and the codings that sample from that random normal with respect to the given log variance and the mean. So where they are trying to create this kind of a latent space or the coding, they have a variational encoder in place where they want this kind of a Gaussian distribution to be invoked or in your underlying latent layers with respect to the how do I say it, those classes. If we are taking this MNIST fashion MNIST example. So that's why we are encoding it via that method, and why when we are trying to sample it, we are using that same technique. We can, of course, use other techniques to make our samples or some other kind of a binomial or other distribution, and then try to sample that. And as uh, Joseph pointed to, yeah, normalizing flows and other bijective functions are some of the state-of-the-art techniques that can achieve the same. Yeah.
Yeah,
So here.
and Joseph, the thing you were highlighting to the left of is what I was reading
That's
from the left top paragraph. Yeah, right there. Yeah.
Okay, so before we get to that, this is just this here, this class, this sampling class. This is where you sample from the Gaussian. This is constructed to sample from the Gaussian distribution with the mean mu, and instead of sigma, he uses the log variance, where let's see, he defines this gamma parameter that is, I forget what it is, e to the sigma squared or something.
Log of sigma square.
Yeah.
It's there on the left bottom of your screen.
Log bar of left bottom.
Right
Yes,
there.
that's right.
Encoder
So
output gamma.
log of sigma squared, and that's so you have the log variance function that he constructed earlier. Anyway, this, if you look at this thing closely, you'll see that it's just sampling from the Gaussian, just the way we talked about it on the previous page. But now let's go to the language that Srinivas was reading from. Is it here?
Yeah.
Okay, so let's start here. Look at the cost function. It's composed of two parts. The first is the usual reconstruction loss. Yeah, that pushes the autoencoder to reproduce the inputs. And we can use cross entropy for this. So we talked about that, about the cross entropy loss. And then the second term is the latent loss that pushes the encoder to have codings that are sampled from a simple Gaussian distribution. It is the KL divergence between the target distribution, which in this case is the Gaussian. So in this case, the choice of the target distribution comes first. And once you know that, then you can construct the KL divergence, right? Because the KL divergence is trying to match something to a target distribution. So the KL divergence isn't where the Gaussian comes from. The Gaussian comes from.
Yeah, the input, one of the inputs is the target distribution, which is the Gaussian, and that's then,
yeah, and where did the Gaussian come from? It's because it's a simple distribution that we know how to calculate. That's the only reason we're using a Gaussian here. because we don't have any other, it's basically the best we can do. If we had some reason to believe that the distribution was not Gaussian, we could use a different target distribution and construct the KL divergence based on that. So that's why he says that this is approximate Bayesian inference and not exact Bayesian inference, because we're only saying that we're approximating the distribution as Gaussian, and then we're going forward with that assumption, and that's not a correct assumption. So that's why he says it's approximate Bayesian inference.
Yep.
Does that make sense?
And yeah, it makes complete sense. And in the next page, we can also see that this sampling class has the inputs of coding mean and the coding log variance being inserted in the encoder. Yeah, in the variational encoder line on the next page.
Okay, I'm at the next page, and then you said there's a sampling class. Ah, here we go, sampling class.
Yes.
Yeah.
Yes. This is the.
So this is the thing that samples from the Gaussian. You just have to give it the mean. You have to give it as an input the mean and the log variance, and then it will generate a sample from that Gaussian distribution. And so the variational encoder just uses that
to encode it in that way.
Yeah. So that's that inner layer of the variational encoder, and so it, at least, we understand what the pieces are, and then he puts it all together, giving it the two-term loss function and so on. So he has a latent loss function here, which is just that equation. I forget what it is. Equation 17.3, the latent loss. Remember, this is the one that has to do with sparsity, with forcing the sparsity low. And then this is the factor of, let's see, is this the half? Okay, so this goes into the latent loss, but then the latent loss gets multiplied by somewhere. It gets multiplied by 0.05, right? Because we've chosen that to be our weight of the loss. Let's see where that comes in. This is just the loss function itself. Okay, and this is basically just implementing equation 17.3. And then he goes through a subtlety, which is that we have to take this latent loss and take the mean of it and divide it by 784 in order to replicate what the binary cross entropy is doing. I think the binary cross entropy is taking the mean over all the 784 pixels. So he says, that you can either multiply this by 784 and then it will compare apples to apples with the latent loss, or you can divide the latent loss by 784 and then it will compare apples to apples with the binary cross entropy. Okay, so apparently, so there's this, so we built the variational encoder, and then there's this add loss, what do you call that? A chaining thing where it knows what you mean. It says add this to whatever your loss function was, and so then you tell it what the normal loss function is. It's this, and now it already has built in that it knows that it's supposed to add this loss function to this loss function, and then he says that the optimizer is RMS prop, and I guess he's discovered that by hyperparameter tuning again. You don't know at the outset which one's going to be the best optimizer. So then this is where he talks about the 784, and then finally you can. So he compiles the model, and then you can actually train the model. So the whole process is is pretty straightforward once you built the variational autoencoder. And I think he mentions a couple of things here. That one is he has to use the functional API. Where is it that he talks about that? Because the computation of the inner layer is not sequential, because you're adding stuff together. So you have to use the functional API. Let's see where he refers to that. Yeah, he says he's first when he builds the encoder part, he talks about that. Let's see. yeah, here he says. Next, we can create the encoder using the functional API because the model is not entirely sequential. And that's because of the inner layer here. This is the part that's not sequential. And then after he builds the encoder that way, then he says, well, we might as well build a decoder with the functional API as well. But we really didn't have to because the decoder is sequential. So that's what he says here. For this decoder, we could have used the sequential API because it's just a sequential stack of layers. But he didn't. So anyway, building the model. And they put an extra, let's see, where is it? The outputs. He built this thing so that it gives you the means and the standard deviations as outputs, although you don't really need them to do the predictions. So that's why when he calls it, he puts a dash for the first two outputs. You don't really care about them. You just care about the codings part. In order to go forward into the decoder, you just need the codings. So then we're done with that. We're done with the autoencoder. Any questions up to here? I know we've already gone a bit over, but the next part is just straightforward. Now you have this beautiful object that is generative. It can actually generate new samples based on the input samples. So he shows how to do that. He says, okay, let's take examples of each class of the, well, maybe there's more than one example of each class because there's 12 things here. But then he says, okay, let's now show how you can interpolate between these things. So he's going to interpolate something between here and here, and something between here and here, something between here and here. And he does that this way. So the ones enclosed in the boxes are the samples from the original data. And then the ones between are the interpolations between. So if you interpolate between a shirt and pants, you get something that sort of still looks like a shirt. If you interpolate between a boot and a shoe, you get something that looks like a sort of a quarter top, sort of a high top shoe, right? If you interpolate between a shoe and what's this? I don't know what this is. Is this a high-heeled shoe? I can't really tell, but anyway, it looks like a bunch of junk right there. You interpolate between a shoe and a dress, you get something that looks like a purse. Maybe because I don't know why that is. Something between a purse, let's see. I don't know why that loop is in there. You're interpolating between a shoe and a dress and you're getting this loopy thing. I really don't know. But anyway, the point is that the network is generating these samples. It's building these samples from its understanding of the data distribution.
I think that the point about the Gaussian, at least for me, intuitively makes sense when you look at certain examples like these. Especially like if you go back to the classical, the VA stuff is that you have a bunch of people with hats, with specs, and you go down to this latent space, and one of these latent space controls your specs, or controls your hat, or control the style of your hair. And now if you tweak that latent variable, you want to still generate that same sort of human being, but without the hair or without the specs or something of that variation. And now you'll get something only close to that if you kind of sample in that Gaussian space, right? If you're kind of sampling in something very different, then the odds that your latent variables will match up will not be very good. I mean, that's kind of the intuitive way that, at least when I was understanding this, that makes sense to me. I don't know if that helps.
I'm trying to think about what you just said. Yeah, so you're talking about the one that generates faces, right? And faces with and without glasses, and male and female faces, and
right.
different colors of hair, different colors of eyes.
Right. So let's say that mu and sigma is like a latent space of 10 variables, 10 numbers, and one of those numbers will control one of those parameters for let's say, eye color. Now, if you change that, you want to change it in such a way that it kind of falls within that Gaussian distribution, and not like really out of that, because then it kind of becomes weird, I think. Like still be as close as, so that you can still get back the face, right?
Yeah. So the idea, I guess, is that locally, even something like this can be considered Gaussian, right? Or something like that. Here's the one with the glasses, and here's the one without the glasses, and so on. If you sample in a Gaussian way locally to here, then you're going to still be within the space of people that have glasses, right? Something like that.
Or yeah, that's what. But that space encodes basically you are a male or a female, so you can tweak that completely, right? All the way to negative or all the way to positive, and that will generate that.
But Nikhil, are you saying that constraining it to like what he shows, right, which is given the images, for example, sticking with his example of the tables that he shows of realist or what actually exists in the image, are you saying that kind of a limitation is useful in generating within the constraints of what faces should still have rather than going away from it? Is that what actually you mean?
That's what my understanding is, yeah.
Okay.
Yeah, so if you tried to sample from people that have glasses and people that don't have glasses, then you're going to get something that doesn't quite look right, you know, somewhere halfway in between with a ghostly set of glasses on or something like that. If you go too far, is that what you're saying?
Yeah, that's what at least kind of makes sense to me. I don't know if intuitively that makes sense. But
and what you said makes sense in this context of what he said before. You said, like, suppose you have 10 different features that have, all the rest of the features are zero or have mostly zero, 10 different weights, right? And all the rest of the weights are close to zero, and there's only 10 that are non-sparse. And then those 10 weights, he says, correspond to features, often correspond to identifiable features, like, in the case you're talking about, hair color, gender, eye color, stuff like that. The network itself selects out those things because of the sparsity constraint. It's forcing you to narrow down to simplest possible set of features that correctly explain the data.
Right, the inherent property of the autoencoder per se. That is what brings it down to something which is in a lower space, but representational of what it is. The variational part is where the Gaussian is thrown in, where now is where you can start generating something. The classic, the main difference between like a normal autoencoder where you will not be able to generate. And changing one of these variables, I think that's what kind of still puts you on this Gaussian, and that's what kind of helps you generate something which is more realistic and still looks like a face. That's what, very loose, high-level understanding from my side.
Yeah. And let's see, the generative part is basically going to be this, right? This piece.
The decoder, right? More than the encoder.
Well,
the decoder.
The encoder is going to.
No, the decoder, right? You change the mu's and the sigmas, and you will get a different.
Right. Yeah, and that's right. That's right. And then you start with these things, and then you dump them in here, and then it produces an image.
Right.
But in some sense, is this also helping you to reconstruct images?
Yes.
Because you're forcing it, you're regularizing it in a sense that you're forcing it to work in the presence of noise. And so that should make you do a better job of getting back the right image.
I think if you don't use noise, I think it's like you're mapping a specific face to a specific face, that same specific face on the output. Or if you talk about MNIST, you're taking a specific 8 angled at a certain orientation, and you're expecting that same 8 to be angled at that same orientation on the output. The moment you throw Gaussian, you're putting in an 8, but you're saying even a tilted 8 is good enough for me because you're changing some of these mu's and sigmas. So it still is an 8, but it's like a generated new 8, which is basically like oriented in a different direction or smaller or scaled or whatever, that sort of a thing.
So you're teaching the network to recognize 8s in a more general way than just from the data that you have.
Right.
Because now it has to be able to recognize 8s when they're noisy or when they're maybe twisted or something like that.
Right. And so hence the Gaussian part of it, at least this is what, I could be completely wrong from my understanding, but this is where the Gaussian kind of helps. It's moving that 8 in these different orientations, different scales, the sizes of the lobes of those 8s, everything is kind of controlled by these mu's and sigmas. And when you add Gaussian noise, it's slightly changing them. So it's still an 8, but slightly moved or turned or whatever that's doing.
Yeah, I think that sounds right. And we've seen this thing before where the network learns the features. Remember when Jeremy was talking about the matrix factorization for when we talked about recommender systems, and he encoded the movies into a vector space with smaller dimensions, and then he examined what the generated features looked like.
Right.
And in some sense, the features had discovered, the network had discovered features like genres of movies that, like when it gave similar encoding vectors, then the movies were like Westerns, or they were violent movies, or they were movies with romance in them or something like that. And nobody told the network about romance movies or violent movies or Westerns. The network discovered these relationships in the encodings that it got from matrix factorization.
Mm-hmm.
You remember that from?
There also, he calls them latent variables.
Yes, yeah, same thing.
Something which you're not teaching the network, it's just learning it. It's hidden in there.
The last segment of what he talks about here is actually interpolating in that latent space, correct? And generating something which didn't exist. It's interpolating not the original images, but the
you're getting
interpolating in the latent space rather than in the actual image original space.
Yeah, and you're getting stuff that in some cases makes sense, in some cases doesn't. Like, interpolating between a purse and a pair of pants, right? I mean, and you get this pair of pants with a halo that looks like the outline of a purse. You're generating new data, but it doesn't necessarily make sense, right? Except he did point to this example where you have a high boot and a low shoe, and then it interpolates and finds like a high-topped shoe, right? This one. And then here he's interpolating, and this whole row is interpolated actually, right? The interpolation between a dress and a shirt looks kind of like a dress.
Mm-hmm. Yeah, the interpolation vector here is kind of weird. I feel like you don't know what's going to happen.
Okay. Yeah, I'm not sure it's meaningful.
Right.
It's just showing that you can generate weird things.
Right. But I'm saying, like, if you take the input vector of the first shirt that is generated and tweak it slightly and then pass it through the decoder, you should still get back a shirt.
Yeah, or if you interpolate.
Yeah, that's true. But sticking with, I mean, I'm speculating because I haven't gone to GANs and stuff, but for example, using what Joseph said too, potentially, again, if you were able to interpret the genre of the movies, which in itself was kind of generated superimposition that Jamie came up with, but assume for a minute that you're able to come up with some vectors, then the generative part is you could potentially, by doing interpolation, the network can generate things that you may not have thought of, right? Like a romantic horror story or something that's kind of weird, which you wouldn't normally combine or interpolate.
Yeah.
But here's a practical use that that you can do. You can say, okay, give me a whole bunch of shirts, give me a whole bunch of labeled shirts, and then start generating an infinite number of, or as many as you want, interpolations among those shirts. And this is data augmentation, right? You can augment your data set by generating new shirts, and then perhaps retraining the network with those new shirts, and then you can do the same thing with purses and shoes and all that. You can do data augmentation using interpolation among objects of the same class. And then you can augment your data set, and presumably that would help you to get a better score.
Like even in advertisement, if I'm not wrong, let's say you take one real high quality image, which costs a lot, then you can break it down into this vector space and then latent space. And then let's say you're able to figure out what the color feature vector is. You change the feature vector on that, so you generate different colors. So you still have high quality images, but they're different colors of your own product. So you don't have to go back and take like multiple images of the same thing.
Yeah, and also it puts face models out of work. You know, all these beautiful women who they use for models in magazines, now you don't need them. You know, you just get a few of them, get a few beautiful women, you have photographs of them, and then just do all kinds of interpolation and generate new versions of them.
One of the older versions of Jeremy has a very interesting a paper where he codes about, it's called Device, I think, where he takes ImageNet, takes all the labels, uses NLP, generates vectors. So you get word vectors, these embedding vectors. And then you combine these embedding vectors with each other. So he does something like, I think, boat and car, he combines them up. And then he looks back in that image space, and then it returns like something like a submarine. So it's like you like combining both the image and the NLP side of things. And that was pretty cool. So yeah, this latent space stuff is pretty powerful.
Well, you've seen that paper that came. I haven't read the paper, but I've seen the image from it where it allows you to do exactly what you just said. It's a combination of images and labels, and so you can say avocado and chair, and it will produce a chair that looks like and is colored like an avocado.
Yeah.
And anything you can say, anything that comes to mind, and it will try to produce an image that has, you know, you can interpolate between, you know, you give it some image characteristics and then turn loose the generative model, and it will generate something that tries to look like what you specified. I'll get that paper and post it on the Slack because it's really interesting.
That is pretty ridiculous.
I just looked at the pictures. I didn't read the words though. So anyway, but yeah, it just came out a couple weeks ago. All right, I think we got a good place to stop. I'm sorry I went over so much, but I think we had a great discussion. And next time we'll get to this really cool topic that I've been wanting to explore for a long time, GANs. So, great, we'll see you on Sunday for that. Have a great rest of the week, everyone.